sake of keeping things on time, even though we have lighter attendance than usual, which is a shame because we have an excellent speaker today. But I think a lot of people will catch up later on YouTube, and I'm sure it's because all of physics is currently in Chicago at March meeting and has been attending talks all week. But so it's my great pleasure to introduce our speaker today, Shelby Kimmel, who's a professor at Middlebury College. Shelby did her PhD in physics at MIT with Eddie Farhi as her advisor. And while she was there, she received the Graduate Woman of Excellence Award. She then went on to do a postdoc at Quicks at the University of Maryland, where she was a Hartree postdoctoral fellow. And then she became a professor of computer science at Middlebury College. So Shelby is one of the rare people who is a computer scientist who can also talk to physicists, having formerly been a physicist, and is, in my opinion, still very much a physicist. In addition to making a number of important contributions to research, theoretical research on quantum algorithms and quantum tomography and things like that, Shelby is also an accomplished amateur Korean drummer. And she's also a skilled craftswoman, which I can show you here. Shelby and I had the pleasure of working on a paper together on quantum seals. Not this kind of seal. I encourage you to look it up if you're interested. And she made this for my kids after we finished it. And it's one of their favorite stuffies. There's two of them actually, and one of my most cherished possessions. So with that, I'll let Shelby take it from here.
Thanks so much for that introduction, Shimon. And it's really a pleasure to be here to tell you a bit about my research. And as Shimon said, part of my research is in designing quantum algorithms, and that's what I'm going to be talking about today. And with that research, I generally think about what would happen if we have a fully working error-corrected quantum computer, and then I figure out what can we do with it and how long would it take to do those things. And since this is an AMO talk, I'm not going to assume that anyone here is very familiar with quantum algorithms, so I'm really going to build up what you need to understand the talk as we go along. But I will say that one of the key subroutines in the algorithm that I'm going to be talking about should be very familiar to most people who work in AMO. So keep an eye out for that. Also, before I get going, I want to acknowledge my collaborators, Jae-yu Jung and Noel Anderson. And they are both undergraduates here at Middlebury College. And it was the summer after their first year that they did this research. So I just want to put out a general plug for any grad students, postdocs, PIs in the audience to encourage you to work with undergrads. I'm at an undergrad-only institution, so I don't have other options, but I love working with undergrads. They really can contribute to research. I mean, these students were writing proofs and analyzing these algorithms, and it's really fun to be training that next generation of scientists. So I just want to put in that plug. And the main work that I will be talking about is with Jae-yu and Noel, but I'll also be mentioning some other recent results with other collaborators, both undergrad and not undergrad. Okay, so today's talk, I'm going to be telling you about speedups for quantum algorithms with easier inputs. So what do I mean by that? So here, the running example throughout this talk is going to be path detection, where we're trying to figure out, is there a path in a maze from an entrance point to an exit point? And what we're curious about is, how do algorithms behave when you have a harder instance versus an easier instance? So I kind of use the words instance and input interchangeably. On the left of the slide, we have what seems like a harder instance of path detection. You can't maybe immediately look at it and know whether there's a path or not if you start to follow the path through the maze, and maybe you take a couple of wrong turns, but eventually it is true that there is a path with the instance on the left, the harder instance, but the one on the right seems to be much easier. You don't even need to, you can look at it in an instant, just see that there's a path, there's a short straight path from the entrance to the exit. So just like with our eyes, we have this easier instance versus a harder instance, and it takes us less time to determine that there's a path in the easier instance versus the harder instance. We would expect that with an algorithm, whether it's a quantum algorithm or a classical algorithm trying to solve this problem, that we should also get a speed up for the easier instance, and it would take more time for the harder instance. And it's not that hard to design classical algorithms that do this. So here I actually just have a very simple classical algorithm that will do better on easier instances and run slower on harder instances for this path detection problem. And the algorithm is you just start from the entrance and you start exploring the maze. So you decide to either go straight or left or right. You do a breadth first search or depth first search, if you know what those are. And you just explore for some time t. And at every step, you kind of take a step into the maze, and then you stop and look around and see if you're at the exit. And if you are at the exit, then you stop and output yes, you found a path. Otherwise, you continue to explore the maze. And after some time t, you haven't found the exit, then you output no. And so this very simple algorithm has this property that if it's an easier instance, like that example of the straight short path, you would kind of immediately go and find that exit pretty quickly, and you'd stop and the whole algorithm would just run in it for a shorter amount of time versus a harder instance or one where there's no path and it's hard to determine that, it would run for a longer amount of time. Okay, and you also didn't need to know ahead of time whether it was an easier or harder instance. The algorithm just kind of naturally detects whether it's an easier instance and runs in shorter time. And so I'm going over this kind of hopefully not too complex example because there are two properties of this classical algorithm that help us to run faster on shorter inputs that we don't necessarily have when we go to the quantum regime. So in particular, one thing you can do with this classical algorithm is that you can check the status of something during the course of the algorithm and then make a decision, do I want to stop now or do I want it to continue running? Also with this classical algorithm, there's what we call a witness of completion. And that is something that you can check that will convince you the algorithm has run for long enough and you have the correct solution. So in this case, if you look around and you see that you're at the exit, that definitely convinces you that there was a path, because the only way that you could have gotten to the exit, because you started exploring from the entrance, you must have followed a path to get there. So that totally convinces you that you can stop your algorithm. Okay, but once we go to the quantum regime, these two very natural properties of classical algorithms don't always hold. And so because of that, it's actually, for many quantum algorithms, it's been harder to figure out how to get them to run for a shorter amount of time on easier inputs. And this is a pretty general problem because a lot of the problems that we want to solve aren't always those hardest worst case inputs. Lots of real world problems are kind of medium or easier inputs. And if our quantum algorithms are having to always run for like the worst case runtime, that is not desirable. So our result was for a very large class of quantum algorithms that I'll tell you a little bit more about as we go on. For this large class that applied to a lot of different types of problems, it was previously, they used the worst case query complexity for all instances. So whether it was an easy instance, a hard instance, you always had to run the algorithm as if it was a hard case instance. But what we do is we create a modified algorithm where if it's a hard instance, it runs with approximately the same complexity as the prior algorithm. So it doesn't do that much worse in those hard instances, very slightly worse. But then if it's an easier instance, we have a much faster algorithm with better complexity. So that's basically what I'm going to be telling you about today. For the rest of the talk, I'm going to start by telling you a bit about the model of computation that we're working in, which is a very common model in quantum algorithm design. So it's kind of interesting to know about. You'll see it if you ever read about quantum algorithms. And then in the middle part of the talk, I'll talk about how we overcome those two challenges that I mentioned in the prior slide, that with quantum algorithms, it's not obvious how you check and then continue running. And a lot of times there's not an easily accessible witness of completion, which means you don't even know what to check. And then we'll end with applications, seeing how does our algorithm do for a bunch of problems of interest. Okay, so I'll tell you about the Oracle model and then we'll pause for questions. Okay, so in the Oracle model here, again, have our running example of path detection. I've now converted it into a graph problem. So we have vertices and edges connecting those vertices, but the problem is the same. There's some start vertex and some end vertex, and we want to know if there's a path from the start to the end traveling across edges. But now to solve this problem, we're given this oracle, which is this black box that you see on the screen, and you can ask it questions about where edges are in the graph. So everywhere you see a dotted line, that is a place where an edge might be present or might not be present. And to figure out which is which, you can ask a question of this box. So you might say, okay, is there an edge at that potential edge 7? And if the box tells you 1, then you know that there's an edge there. You might ask, is there an edge at position 3? And if the box tells you no, you know that there's no edge there. So at this point, even though we've only asked 2 questions, we actually already have enough information to say there was no path, because you can see now there's no way to get from that starting vertex to the ending vertex, even if all the other edges are there. And so this is what, like, our goal in this oracle model is we want to solve our problem, but we want to do it while asking as few queries of this box as possible. And you can see that sometimes you can get away with asking very few queries before being able to answer the question. And in this model, where any other operations that we have to do besides this black box are free, which means we're not counting them. We're just counting uses of this box. And this is a natural model for computation, especially in instances where you maybe have a function that's really hard to compute, and then you want to minimize the number of times you have to compute that function. Also, for a lot of problems of interest, the number of times you have to use this box basically scales exactly the same as the total runtime. So when we understand how many times we have to use this box or this oracle, that tells us about the runtime. Also, when we ask questions of this box, the way we say that we're asking queries. So I'll talk about querying the oracle means asking a question of the oracle. Okay, so just a little bit more formally, the problem is we want to create now a quantum algorithm that will evaluate a function f, and it's just a Boolean function. So our quantum algorithm should either output a 0 or a 1. For example, the function that we might want to evaluate is there a path? And then what we're given is an oracle that tells us about, like in our example, where the edges are. So there are many instances depending on where the edges actually are. There might be some instances where the configuration of edges might make it hard to determine whether there's a path or not, and some where it's easier. And now I've kind of written this box down here. The input we're thinking about it as a quantum operation. So it takes in 2 quantum registers. The first register is kind of asking the question, like which edge you want to learn about. And the second register is where we're going to store that answer. And then the box, really what this box is now is a unitary, which transforms quantum states to other quantum states. And now it stores the answer to our question in the second register. And because this is a quantum unitary, we can ask it questions like this, like we can just ask it whether there is an edge at position I. But what we can also do is we could ask it questions in superposition. So we could ask it, in superposition, are there edges at a whole bunch of positions? And then we would get those answers out, but also in superposition. Okay, now our goal is to evaluate this function, whatever the function is, using as few queries as possible. And we want to do it using as few queries in the worst case over all possible instances, but then we would also, for those easier instances, like to use fewer queries. And just kind of some notation, when I talk about the number of queries, I often talk about query complexity. Those 2 things are the same thing, the number of queries required to solve this problem and the query complexity. I will sometimes use the word runtime. Runtime tends to refer to the time that an algorithm takes, which includes both the number of times you would use this unitary and any like additional unitary operations that the algorithm would require. But I sometimes use those interchangeably, since for a lot of problems of interest, they're the same. And especially for an audience that's a little less familiar with query complexity and these oracles, like the runtime is a more kind of understandable term, I think. Okay, so that is the model of computation that we're working in. And now we're going to next move on to designing our algorithm and figuring out how to get it to run faster on these easier instances. But I'll pause to take any questions.
Great. So yeah, there are a few questions. So first of all, how hard is this problem sort of just in general or classically? I mean, and is that something that you can specify, that this is like, you can solve this in polynomial or exponential time or something like that, or is it?
So for this path detection problem that we've been using as our running example, that classically, I mean, if you have n vertices in the graph, they're at most n squared edges or big O of n squared edges. So in the worst case, you'd have to look at all of them to determine if there's a path. And in fact, you can prove that classically you would have to use n squared queries and n squared time in the worst case. But so you can see we're talking about polynomial, like the graph itself is of size n squared, and then we're getting an n squared classical algorithm. In the quantum case, we'll talk a little bit about what the runtime is later, but it's only a polynomial speedup, kind of more of like a Grover type of speedup rather than like a Shor's algorithm exponential type speedup. I mean, we're kind of talking about like these everyday problems that you might want to solve with a quantum computer, like just like how, we're not trying to do something factoring that has this very specific like targeted cryptography application. This is just something like computers solve search problems and path detection problems as subroutines very commonly. And so this is like, once we have these working quantum computers that are hopefully doing more things on a daily basis, we'd like them to do these easier problems faster. And also, especially if they're easier instances of those easy problems, we'd like them to do those much faster, ideally.
Got it. And then another question from Lindsay actually is, in the original Oracle slide, which I think you're showing us, or maybe, yeah, basically here, only some links were connected. How generic is the operation? Do you have to consider all links, or is there a reason to think there are sometimes subsets?
Yes. So we're going to see this a little bit more later in the talk. A lot of times you just want to consider generic graphs where any possible edge could exist. But it turns out that you can encode a lot of other interesting problems within this one problem if you allow for like only subsets of edges to exist. So we're going to see that again a little bit later.
Okay, and maybe I'll ask one more question and then we can move on. So in the very first example that you gave us where you were showing mazes, you sort of suggested, that you would run something for some amount of time t, and then if you kind of don't find the exit, you just say no. But it's not clear that maybe in that case there was one, but you just didn't get there in time if you'd made t a little bit longer. It seems like here, as you said, in this graph case, that's not true, that we can know with certainty once you've checked all n, once you've checked all possible vertices or edges, for sure. So is that the correct way to understand that in this problem, you can know whether or not there really was an exit eventually or a path?
Well, I guess there are two ways of answering that. The first is that with that t, like if you did a breadth first search, we know exactly how long that's going to take to explore the entire maze. So we could say, if you haven't found the exit after this time t, then you know for sure that there's not an exit. But actually in this Oracle model, maybe one thing that I didn't mention, I mean, quantum algorithms in general are probabilistic algorithms, which mean we allow them to fail on some like 10% of the time. Not 10% of inputs, they just, on any given input, they can be allowed to fail some of the times that they run. So you could also imagine an algorithm where there is that time t, and maybe sometimes you're wrong. Like if you output no, but maybe if you'd explored a little bit longer, you would have found it. So if you had a probabilistic classical algorithm that was probabilistically exploring the maze, then yeah, you would be wrong some percentage of the time. But if you adjusted t, you could make it so that your tolerance for error was small.
And sorry, just to clarify, so that probabilistic nature of quantum algorithms, this is not sort of some issue with errors and fault tolerance or something. This is purely because at the end you measure and you project some superposition into some specific set of eigenstates or something.
Yes, exactly. It's not to do, the errors that I'm talking about are not to deal with errors in the system. This is even if you have a perfectly working computer according to all the rules of quantum mechanics without any need for error, it's not because the qubits are not good qubits. Even if we had perfect qubits, it's just we have like a superposition and there's some probability that when you measure, you collapse in the wrong state.
Great. Okay, I think we can keep going.
Okay. So I mentioned that there were these two challenges for us in trying to create a quantum algorithm that will have an improved runtime or an improved query complexity on those easy instances. The first is that it's hard in a quantum system to do kind of a check and then continue running. And then there's also this issue of not having a witness of completion. And it turned out the first issue itself is a very easy issue to overcome. The second challenge is a bit harder. So I'll discuss those now. But so let's first talk about this kind of easier challenge that quantum mechanically it seems like you can't check and then continue. And this is really the issue that quantum mechanically it's hard to do program an if else into your computer. And classically, this is easy. Programming code with an if and else statement is like one of the first things you learn, one of the first things we teach our computer science students here. But quantum mechanically, we can't really do this, because as soon as you do an if, you need to check something about your algorithm. And to check something about your algorithm, you have to measure it, because we have a quantum system. And as soon as you measure it, then the whole system collapses. And once it's collapsed, you can't just pick up and continue your computation where you left off, because the computation is not there anymore. So this basic building block of classical algorithms is not available to us. But turns out there's a somewhat easy way to get around it. You just iterate the algorithm and run for increasingly long periods of time. So the first iteration, you would just run for, say, 2 seconds, and you would stop and measure, and hopefully that measurement would tell you whether you can stop running. But if you measured and it said, oh, no, you have to run for longer, we're not at the end yet, you can't just keep running. But what you do is just in the second iteration, you start over from the beginning, start your whole computation over, and now run for 4 seconds, measure, you destroy your computation, see if you needed to run for longer. If you did need to run for longer, then now you run for 8 seconds in the next iteration, starting all the way over. And then in the worst case, after just log t iterations, you'll run for that kind of worst case runtime. And by the magic of the geometric series, even though we're not continuing after any time we stop our computation, we're always starting over, we end up still with the same total runtime of big O of t. But now getting to this issue of errors, if just naturally, we generally consider quantum algorithms that have some probability of error, like 10%, say. Now that's not good enough for us, because that means we'll, with high probability, have an error on one of these iterations, and then we're going to almost always get the wrong result. So we do have to do a little bit of error correction, and that increases the runtime by some logarithmic factors. So when you see this little tilde over the big O, that means I'm suppressing log factors. So it means the runtime is basically the same as it was before when you do this whole process, but with some extra log factors. So that's what that means. Okay, but this is, like I said, this is actually not that much of a challenge. But the bigger challenge is when you stop and make a measurement at this point, how do you know if you're done? Where is there a witness of completion that you can rely on? Okay, so let's talk about that. The second issue, how do we find a witness of completion? Okay, and I've been talking kind of quite generally, but let's talk a little bit more specifically about how this algorithm works. So I said that our result applies to a large class of quantum algorithms. And in particular, it applies to this class of algorithms called span program algorithms. And span program algorithms, it's really more of a design paradigm. So if you're familiar with, say, greedy algorithms for kind of standard classical algorithms, that's just a way of thinking about how to design algorithms. So our result doesn't apply to any specific algorithm. It applies in general to this whole approach for designing algorithms. So that makes it a pretty kind of powerful and generalized approach. And so the span program design paradigm, these span program algorithms themselves are very powerful. So it turns out that for any Boolean function that you'd want to design a quantum algorithm to evaluate, there's always some span program algorithm that has the optimal query complexity, the optimal number of queries for those worst case, hardest inputs. It might not always be it might not always be easy to find those best case span program algorithms, but what we do know is that there is always an optimal span program algorithm out there for any function you want to do. So these span program design paradigms, it's basically a universal optimal paradigm for designing quantum algorithms. And so because of that, people have studied these a lot, and they've come up with all sorts of algorithms using this paradigm. But for all of these algorithms that people had designed, they always ran for the worst case runtime, for the worst case query complexity, no matter the input. They never could run faster for those easier inputs. Except that there is this kind of weird caveat that a lot of times these algorithms in these papers, people would say, okay, well, if we knew ahead of time that the algorithm is easy, that the input is easy, then we get a speed up. And this to me was just, this is a very strange thing to say. Like, how would you know if you know ahead of time that the thing is easy, don't you know something about it already? That it seems like cheating to be told ahead of time that it's easy and then know that you can run it for faster. So our goal was to get rid of this kind of putting the cart before the horse promise, and we just wanted to automatically be faster for those easier inputs. Okay, so to tell you about this next part, we need to talk a little bit about what's going on under the hood of these span program algorithms. And the key subroutine is phase estimation, which is hopefully something that is somewhat familiar to many AMO folks. So with phase estimation, we have a unitary U and an eigenvector psi. And so psi has a complex eigen value, e to the I lambda, and we call lambda the phase or the eigenphase, or just the phase of that eigenvector. And our goal in phase estimation is to estimate the value of lambda. And so here I've done some tick marks on an axis. Lambda is always somewhere between 0 and 2 pi. And I've put tick marks at increments of 1 over theta. And the way that phase estimation works is it gives you an estimate of lambda that's basically kind of put to the nearest, basically, increment of 1 over theta. So in this picture at right, what I'm trying to illustrate are the probabilities of getting different outcomes. So you're kind of very likely to get 4 over theta or 3 over theta if your original phase was somewhere between 3 over theta and 4 over theta. And kind of the way this algorithm works in the context of these span program or algorithms is that in order to implement U and do this phase estimation, U requires uses of the oracle. And so if you know about phase estimation, the more accurate you want to be able to estimate your phase, the more times you have to use U, which in our case means the more times you have to use that black box, and your query complexity goes up. And so here, if theta is a parameter that we're using to say how precise do we want our phase estimation to be, so you can see if theta increases, we're going to have more tick marks, and we're going to get a more precise estimate, but we're going to do that at the cost of more queries. Okay, and then with the standard span program algorithm, it's actually the whole algorithm relies on phase estimation. And what you do is you just run phase estimation. You've kind of crafted this unitary, and you have not quite the eigenvector, but you have some state that has some overlap with eigenvectors of certain eigenvectors of the unitary, and you run phase estimation. And if you get an output phase of 0, then you interpret that as yes, like the function that you're evaluating should be yes, like yes, there is a path. And if you get an output phase that's not 0, then you interpret that as saying that there's not a path. And kind of the thing to notice here is that it's not really obvious what a witness of completion would be. Like, say you ran this for a short amount of time and you run phase estimation, you're still always going to get either a phase of 0 or a phase that's not 0. Like, do you know, was that a phase of, should you interpret that phase of 0 as a yes? Should you interpret that phase of 0 as a I haven't run for long enough? There's no additional information here for us to base our witness off of. So we're going to have to kind of go inside the algorithm and tweak things a little bit to see if we can pull a witness out of this subroutine. Okay, so we want to have an algorithm that runs with less queries on those easier inputs. And I've said that I've kind of given us only one knob to turn so far. The only way to have an algorithm that runs faster is to reduce the precision. So that's what we did. Let's just try to reduce the precision and see if we can make things work out. Okay, so in the yes instances, so if we want our function to output yes, we had said that that's when we should get a phase of 0. And so what we found is when we reduced precision and ran this algorithm, and also we had to tune a couple of other parameters to make things work out. I'm doing a little bit of simplification here. But what we were able to do was we were able to show that, okay, whenever we have a yes instance, even with the reduced precision, and I'm kind of illustrating the reduced precision, you can see there are fewer tick marks here. They're more spread out. There's always a phase that's very close to 0. And then when we run phase estimation, we get an output phase of 0, and that's good. That's what we want. Okay, but what we found was that when we had these hard no instances, so when we want our algorithm to output a phase that's not 0, what was happening was that we were having low-lying eigenphases. And then when we ran phase estimation, we were getting a high probability of outcome 0. And actually, basically you couldn't, these two cases were indistinguishable when you look on the right-hand side in terms of the output probability. So this is exactly what we didn't want. When we had this low precision phase estimation and no output zero, we're unable to distinguish between yes and no. And it's not really clear what witness we could use to distinguish between these two things. And just kind of as a brief aside for people who are more familiar with the kind of quantum algorithm version of phase estimation, you do not only learn an estimate of the phase, you do also get a quantum, a state that is close to one of the eigenstates of U with the phase that you kind of collapse to. So it's possible that we could extract some information from that approximate eigenstate that is produced as kind of a side effect of this algorithm. Although it turns out that, even just analyzing the low-lying eigenvalues of this unitary U is quite complex. Trying to understand what those eigenstates are is like even harder. So this is something that we're working on with upcoming work. But it turns out we don't even need to delve into this to get our current algorithm to work, because what we found is that even though with hard nose, we have this issue where we can't distinguish, with easy nose, what we found was the phase was really far away from zero. And so when we run our phase estimation algorithm, in that case, we got an outcome that was not zero, and we got the right answer. So if we have low precision and we had an output that was not a zero phase, we were confident that the instance was a no instance. And so now if we put this all together, that's actually enough to get an algorithm. So what we do is we run our phase estimation, span program phase estimation algorithm with exponentially increasing precision. And at each iteration, if we ever see an output zero, we don't know how to interpret that. So we just rerun again with more precision the next time. If we get a non-zero output, then we know that's the one case that we kind of were confident that we should have a no outcome. So we stop and output no. And this gives us a faster runtime for all those easy no instances. And those easy yes instances, what we were able to do was we were able to find a negated span program. And what that did was it exchanges yes and no instances while preserving their difficulty. So this negated span program took every yes instance and turned it into a no instance, and every no instance and turned it into a yes instance. But all those easy yes instances got converted into easy no instances. So the whole algorithm together is we, with exponentially increasing precision, run our original span program, the original span program phase estimation algorithm. If we get a non-zero phase, stop and output no. Then we do the negated, and if we get a non-zero phase, we stop and output yes. Otherwise, we just go to the next round where we increase our precision. And so now this gives us everything we want. We have faster algorithms for those easy yes and no instances. And in the worst case, we only increase the runtime or the query complexity by a logarithmic factor, which just comes from that geometric scaling that I talked about earlier. Okay, and I'll say, I have simplified things a little bit for the purposes of this talk, but this is the gist of what's going on. Okay, and so just now we can actually talk about the performance, and this is kind of maybe the most mathy looking slide, but once we have this down, then we can actually start to apply it to interesting problems and see how it does. So bear with me through this one. So when we design these span program algorithms, what happens is for every instance, like for every possible maze, the span program produces, or you can analyze the span program to determine that instance's witness size, which we denote by W of X. And then the original span program algorithm, it's query complexity scaled like the expression that I have here. And so you can see immediately where this worst case behavior is coming from, because we're taking the max over all yes instances and the max over all no instances. So we're basically taking the witness size of the hard, and this witness size is basically corresponding to the difficulty of the instance. So we're basically taking the size of the difficulty of the worst instance in the yes case, the size of the difficulty of the worst instance in the no case, and multiplying them together, then you take the square root. So the square root is kind of the quantum part of things. You get a lot of square root of n complexity for quantum algorithms. The whole thing is quantum, but anyway, in the case, and this is now where that promise version came in. So a lot of these algorithms, or a lot of these analyses of span program algorithms would say, okay, well, if this is kind of bad because we see that we have these worst case complexity, but suppose that you're promised ahead of time that you are only going to have yes instances that have some witness size that's less than W. Well, then that whole max, the worst case it's going to be is W. And so you get a scaling that's improved, but you had to have this promise ahead of time. So with our algorithm, we get rid of that promise. And instead of having to take this max over all yes instances, if you happen to have a yes instance, you just get to plug in the actual witness size of that instance. So if it's an easy instance with a small witness size, the query complexity just scales directly with that. And so you can see the form of this is very similar to the form of this, except we've just removed this promise. We just get it to run without the promise in the kind of desired amount of time. We still have, if the actual input is a yes instance, we still have a term that's a max over all no instances. Likewise, if the instance is a no instance, we take the witness size of that no instance times the max over all yes instances with the square root. And the other difference here is that we have a tilde from our kind of those log factors from this error correction with the geometric scaling. Okay, so we now have all the tools we need to analyze how it's going to do on path detection and show how once we can analyze path detection, we can actually learn about its behavior on all different types of interesting problems. But before we get into those applications, I will pause again and answer questions.
Great. So Elizabeth asks, when you say easy, does that mean easy for a classical algorithm also? That is, if it qualifies as easy, should it just be run on a classical computer? Is it ever easier to design a quantum algorithm to determine easy versus hard instead of just solving the whole problem?
Yeah, those are a lot of really good questions. So I think one thing that we'll see once we actually see some examples is that what's easy for a quantum algorithm is not necessarily what you would think of as being, sometimes it's what you would think of as being easy for a classical algorithm, but not necessarily. Although what it seems like is that the quantum algorithm includes, at least most of the things that I've looked at, the quantum algorithm includes those ones that would be easy for, the quantum includes things that would be easy for classical, but also seems to include some extra ones that seem to somehow take advantage of some quantum structure that maybe the classical algorithm couldn't take advantage of. So it seems like it's mostly, you would get an advantage using a quantum algorithm for those easy inputs. And in fact, problems that weren't easy maybe might now become easy if they have certain structure that the quantum algorithm can particularly take advantage of. Sorry, there were several questions. If there was more.
Yeah. The other one is it ever easier to design an algorithm to just determine if it's easy versus hard instead of solving the whole problem?
Yeah, so there are algorithms that do that, and they are a bit slower than ours. So it's kind of, somehow that seems like a little bit of a harder problem. I mean, ours does give you some information about how hard or easy it is, because if it's easy, it ends early. The problem is ours could also sometimes end early on harder instances. And so it's not necessarily telling you, it's kind of only tells you one way, whether it's easy or hard or not. Yeah, it tells you if it's not hard, I guess, or not easy. Anyway, I get a little confused.
Okay, so I have a question. So you mentioned that it's not always easy to design a span program.
Mm-hmm.
So if you have one, like you do in this case, it seems like, is it easy to design that negated span program that your algorithm requires?
Yes, that's the negation part is not too challenging. I mean, coming up with how to do the negation was not maybe, it involved a little bit of thought, but once you have it, yeah, it's kind of, it's not very hard to do. I will say there is you can just solve, if you have a problem, there's an algorithm that produces an optimal span program algorithm, but it runs in exponential time or something like that. So of the size of the problem that you're interested in. So it's not efficient.
Okay, I think we can probably keep going to the applications.
Okay, So yeah, thanks. This has all been very like a little bit abstract so far. So thank you if you're still here with me. I'm gonna we're gonna bring it back and talk about an actual application on a very small, simple graph. So here we have our favorite problem, path detection. I've replaced the start vertices and end vertices with S and T, which is kind of just more standard. In computer science, this is often called the ST connectivity problem, but it's just path detection. Okay, and so we want to figure out how is our span program algorithm going to do? What instances are going to be easy? And to figure that out, we need to calculate these witness sizes, that function W of X. And what's pretty cool about this for this path detection problem is the effective resistance, the witness size is exactly equal to the effective resistance of the graph. So what do I mean by that? In the case that we have a path, what we're going to do is we're going to imagine interpreting this graph as an electrical network where we're going to put wires everywhere that there's an edge in the graph, and we're going to attach like a 1 ohm resistor onto each edge. And then we're going to imagine attaching a battery between S and T. And then we can ask, what is the effective resistance of this network? And so in this case, if we have this particular instance with 0, 1, 1, that corresponds to no edge, 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 then because we have two resistors in parallel, we get an effective resistance of 1/2. Okay, so that's done for one instance. Now we can say, okay, well, what happens if we now have only one edge? So we've removed that middle edge. Now the effective resistance is 1. Okay, and so this kind of makes sense. I said that this effective resistance should kind of scale with how difficult the problem is. If we're trying to find whether there's a path between S and T, it should be easier if there's two edges. It's easier to find one of those edges. And so here we see that the witness size is 1/2, which is smaller than 1, which is what it becomes when you only have one edge. Okay, what about when we have a no instance? So when we have a no instance and there's no edges, or there's no path, then what we're going to figure out the witness size. Everywhere there's not an edge, we're going to put a wire with a capacitor on that edge, and then we're going to imagine again attaching S and T to a battery, and now calculate the effective capacitance between S and T. And in this case, because capacitors in parallel add, we get that the effective capacitance is 3. Okay, so hopefully all you physicists can use your E&M knowledge you could go around and calculate effective resistance and effective capacitance, and then that would tell you about the query complexity of this path detection problem. Okay, but let's try to use this to solve something interesting. Let's consider a graph where we just have n edges connecting potential edges, we don't know if they're there yet, connecting S and T. This is essentially Grover search put into a graph problem, because we're just asking, as long as there's some edge somewhere, we're going to say, yes, there's an item. And that's similar to Grover search. We're trying to say, is there a 1 anywhere in my list? Is there a marked item anywhere in my list? And here, a small difference with Grover search, a lot of times we're trying to find the location of that item. In this case, we're just trying to say, is there a marked item in my list? You can see these two problems are, pretty much equivalent. And so then we can say, okay, well, suppose there were m edges in my graph. Well, in that case, we could again calculate that effective resistance, and we would get 1/m using the rules for resistances in parallel. And still, if now there are 0 edges because of the rules for capacitors in parallel, we would get a witness size for the no case of n. Okay, now just to remind you, we had this equation, which was the query complexity of our algorithm. And so if we do happen to have a path, if there are marked items in this graph, then our algorithm, you plug in the witness size of that yes instance times the max witness size of the no instance. The no instance is n. Our yes instance is 1/m if there are m edges. And so putting it all together, what we find is that if there are m out of n items that are marked, we can solve it in big O tilde square root of n/m queries without knowing m ahead of time. And this is actually a well-known result in quantum algorithms. So this is not a new result, but what's kind of interesting is that we match basically the existing best known algorithms for Grover search when there are multiple items. But prior results, there's this first result from Boyer, Broussard, Hoyer, and Tapp. They also have kind of log factors in their approach, but their approach is highly search specific. So it only really works for Grover search. Whereas our approach is very general, and not only does it work for this type of graph, it works for any type of graph that you plug in. Not only does it work for path detection, it works for any span program algorithm that you might design. I will say there's a slightly improved algorithm that gets rid of this tilde from Yoder, Low, and Chong. Theirs is also highly search specific and not, as far as we can tell, generalizable, although that's something we're looking into. Okay, but the point is, this seems to do well. It seems to do as good as Grover's. It should at least do as well as the best that we could do on Grover search, and it seems to be doing that. Okay, but now we can think about applying it to other types of problems. So here's another way that we can solve a problem that is not path detection, but with path detection. So here we have a graph with just 5 edges, and we might want to figure out, is there a cycle in this graph or not? And it turns out we can convert that into this cycle detection problem, where basically what's going on here is that if you look at this left kind of part of things, this is asking, is there a cycle in the graph and does it pass through edge 1? The next part is saying, is there a cycle in the graph and does it pass through edge 2? Because if it passes through edge 2, it's basically like edge 2 is there and also there's a path. So that's where that reduction to path detection comes in. But now we can use the tools that we have and we can calculate the effective resistance and the effective capacitance of this graph, this ST connectivity graph. And what we find is that we can detect whether a cycle is present in this runtime n to the 3/2 over square root of c, where c is the number of cycles. In fact, it's the cycle rank, which is basically kind of more general term for the number of cycles. And again, you don't have to know C ahead of time. So this is kind of maybe getting back to Elizabeth's question, like you would hope that quantum algorithms are getting a speed up in cases that we would naturally consider to be easy. And that's exactly what we see here. Like if there are many cycles in the graph, you would expect that the quantum algorithm should find it faster. And so this is kind of a good sanity check that yes, that is what's happening. But maybe back to your more general question, like we're seeing that quantum algorithms are able to solve this problem faster if the instance has small effective resistance. And if you think about effective resistance is small if there's a short path, and you would expect that a classical algorithm could also take advantage of a short path. But effective resistance is also small if there are many long paths. And that's because of the way that effective resistance in parallel kind of inversely adds. And that is not necessarily so clear how a classical algorithm would take advantage of that, but somehow the quantum algorithm is able to take advantage of that information in parallel. It's not literally like flowing, there's not any literal circuit, electrons flowing in this algorithm, but the math just turns out to be the same. But it's pretty interesting. It's kind of, I don't know, it feels very quantum-y to have these parallel paths that the quantum algorithm can take advantage of. Okay, I'll give one more example of how broad this, I've only been talking about path detection, but really you can do a lot with path detection. Here's a problem for formula evaluation. So here we have a Boolean formula, which is just a bunch of ands and ors and negations. And it's kind of in this query model. So you could ask, is X1 true or false? Is X2 true or false? And you'd like to evaluate whether the whole formula is true or not by learning as few of these Boolean variables as possible. And so that Boolean formula is exactly equivalent to the graph that's on the right. So if there's a path on the right, that only happens if and only if the formula is true. And you can kind of see what's going on here. Like we have this first clause that is an and, x1 and x2. And here we can see that we have x1 and x2 connected in series. And there's only going to be a path if both of them have edges, right? So that's encoding kind of a logical and, that the path has to go through both, so they both have to be present. And then things going in series, in parallel, are encode logical ors. So you can take any Boolean formula, convert it into SD connectivity. And in this case, I think it's not totally clear to me, like if this graph has smaller effective resistance or smaller effective capacitance, that means somehow that it's easier to evaluate that formula. But like what, I'm not sure classically, like what does that mean about the formula that it's easy? So that's something that I think we're still trying to understand. Okay, maybe we're running, I won't talk about this. If this is we generalize our approach to a much more general problem where you're not just trying to output yes or no, but you're trying to create a quantum state. And we are able to do this kind of a similar procedure with a couple of challenges, but maybe if people are curious, I can talk about that. And I'll just close by talking about some of our future and current work related to this. So I think the most exciting thing that this result and work opens up is the opportunity to study average case quantum algorithms versus average case classical algorithms. So the majority of work comparing quantum algorithms and classical algorithms has been comparing how do they do for those very hardest worst case inputs. And partly that was because for a lot of quantum algorithms, we just didn't know how it behaved on average because we didn't have an algorithm that did much better on those easier cases. Basically, Grover's search is one of the only algorithms for which we had this easier case analysis. But now, you know, a lot of real world problems are not worst case. For natural problems, you can look at what's the real world distribution of easy and hard instances, and you can now calculate how would the quantum algorithm do on average versus how would a classical algorithm do on average. And what's particularly interesting is that there are examples where you can get, where in the worst case, a quantum algorithm only does polynomially better than a classical algorithm. So like maybe a square root speed up in the worst case, but you can craft these distributions such that on average, the quantum algorithm does exponentially better than the classical algorithm. So it could be that even in all these problems, like, oh, Grover's search, it doesn't seem like it's that big of a speed up, you know, potentially there's kind of hidden in there, if you pick the right distribution, a kind of exponential speed up in there. So that's something that I'm really excited about exploring. Part of what makes this a little bit challenging is what we were talking about earlier, which is that, like, we've seen that with graphs with small effective resistance, we can understand how the quantum algorithm behaves, but it's not totally clear how the classical algorithm behaves. We'd like to say that there are these graphs that have small effective resistance, but that it's kind of hard for a classical algorithm to do well on them. And we have certain very specific examples where we can analyze that, but having this is basically a purely classical computer science question, like, what's the best classical algorithm on the graph that has small effective resistance? I mentioned that there's this approach for Grover search using, they're called these fixed point methods that gets rid of those extra log factors. We'd like to see if we can, those little log factors are a little annoying, so we'd love to get rid of them. Maybe these approaches can be generalized. Also, we're interested in kind of getting more out of this phase estimation. There is a quantum state that's produced. Can that act as a witness? What other information can we get out of it that might just help us develop new quantum algorithms? So with that, I'd like to thank you for your attention. I'd like to thank my collaborators and my funders, and I'd be very happy to take more questions.
Great, thanks for a great talk, Shelby, first of all. So there are some questions here. So first, if I understand correctly, these algorithms find that there is a path. Is that true, or do they also find which path is the one you want to use?
Yes, so these algorithms only detect whether there is a path or not. And so that's actually part of that witness state. Like, it should contain some information about the path. Like, basically, in certain instances, you can show that it is maybe like a superposition of edges that are kind of on the path or on the multiple paths if there's kind of multiple flows through the graph. But figuring out how to ensure that that's the witness that you get, and how to then use that to give you something useful, because when you make a measurement, it collapses. That's something that we are currently working on.
And then, so can you describe sort of, I think you gave a couple of examples, but can you describe a real world problem where you only care about whether there's a path rather than caring about which particular path you want to take?
I mean, I guess maybe like a formula evaluation, I guess the goal is to say if it's true or false. It's a good question. Sorry. I'll have to get back to you.
Okay, I thought that's a clear example. So then, okay, I have a question too. So is there you kind of already mentioned this and hinted at it, but is there an intuitive way to understand this sort of circuit resistance capacitance mapping? Is it just a like kind of just the math works out the same way, or is there something more there?
Yeah. I mean, what's kind of going on is that U is somehow encoding information about a quantum walk on the graph. And then we're kind of learning properties of the kind of eigen structure of like eigenstates of that walk. But like the way this algorithm works, we're just doing phase estimation. So we're not actually doing a quantum walk. So, I mean, this is, I guess, a question that is definitely worth pursuing. At the surface level, it's just that the math, it's exactly the same math. And so that's where it comes from. But yeah, I think underneath there is probably a deeper connection that could be explored.
Great. And maybe I'll ask one more related question. So it seems like so far, each path sort of has a resistance or capacitance of 1, which I guess comes from your oracle sort of returning a Boolean or something. But is there a version of this that sort of maps to analog values, more like traveling salesman or something like that? Or
well, actually, yeah. So for simplicity, I've just said that all of the, you'd always put like a 1 ohm capacitor or one equally sized resistors or capacitors. But what you could do is ahead of time, if you knew the structure of the graph and you knew that like one edge was really important, you might want to put extra weight on that edge and give it a higher resistance, say. And it turns out that for certain problems, to get the best complexity, you do need to scale that, but you would do it ahead of time. And then you would still calculate the effective resistance and the effective capacitance, where I think that for the effective capacitance, then you'd do 1 over whatever that number was on that edge. So yes, I've only kind of given more simple examples where you don't need to do any of that scaling, but in general, you would to get an optimal algorithm.
Great. Okay, well, I think we're right on time. So I want to thank Shelby one more time again for a really interesting and very clear talk. And then I want to announce quickly that our speaker in 2 weeks, the next Vamos, will be from Tara Fortier from NIST, who will be talking about time and the precise measurement and application of atomic clocks. And then the only other thing I'll say is that if you want to join Shelby now for a post-seminar discussion, you can do so at the link that I'm about to post in the chat. And I'll also post it on YouTube. And I think Shelby will join there. And thanks again, Shelby. That was really interesting.
Thank you.